In continuation to the applications of solubility product, we said a better way to do quantitation other than gravimetric analysis, where you do the weighing of the precipitated salt, is actually to do what you call the volumetric analysis. And this is a technique, most of you know about it, in which the volume of a standardized solution in a burette is used to react, with an unknown amount of analyte, that is present in an Erlenmeyer flask. And if the stoichiometric relationship is known between the reaction of the titrant, which is here, and the concentration is known, and the analyte, that is present, then we can actually determine the concentration of the unknown. Okay, and we normally use a burette, but lately, of course, with advancement with instrumentation, burettes are falling out of favor, and instead you're gonna see the titrations have been automated using these instrumentation called auto titrators. So in the industry, you're gonna find in most cases people use auto titrators, to do volumetric analysis or titrations. It's very important, to remember that when you are doing titrations, the K, the equilibrium constant, has to be fairly large. Meaning, your reactants, which often, is plus your reactants, going to the products. The KSP needs to be very, very large. Okay, and of course your reactant in this case, would be your titrant, whatever is coming from the burette, that is, plus your analyte, that's your reactant really, going to whatever the products. All right, so that is the K that we are talking about. And like I say, the stoichiometry is known, so if you know the number of moles of the titrant reacting with the number of moles of the analyte that you don't know the concentration, then you can do a mole equivalent kind of calculation and determine the concentration of the unknown. Now remember, when you're doing titrations, you're looking for the equivalence point. And the equivalence point is a point at which you've added enough known volume of the titrant, which the concentration is known anyway. And those number of moles that you've added equate to the amount of, or to the moles of the analyte that is present. And so the reaction has gone to completion. So in essence, we are saying equivalence point is a point at which you have consumed all the analyte, by adding enough titrant, which its concentration, for the product, to be formed. And remember, like I said, the K is very large. So for every drop of the titrant you add, it will very quickly react with the analyte to give you a product. And that way you're going to have an equivalence point. Okay? Hope it's clear. The point at which you've consumed all the analyte is what you refer to as the equivalence point. Now, whatever you see, whatever the detector sees, in most cases, if you are doing a burette, of course, the detector is your eye, and it sees a color change. So whatever you see is what you refer to as the end point. But remember, an end point, is always erratic, because the end point requires you to add a little more titrant, than you need to react with the analyte for you to see the end point. And so the titration error, really, which is inescapable if at all you're doing the color type of indicator titrations, is, the end point. The color that you see, the point at which you see the end point, the volume at which you see the end point. minus the equivalence point, which is the theoretical point, at which you've added enough titrant, is referred to as a titration error. Having said that, you can actually escape the titration error if at all, you use potentiometry or instrumentation as another way of doing the detection of your equivalence point. For example, if at all you're doing, and I'm going to give an example later on of the solubility product, but if you're doing acid-base titration, you can use pH electrode as a way to determine the equivalence point. And because you're using a sensor, in that case, there is no titration error. All right, so take note of that. If at all you're doing potentiometric kind of detection for titration, you can get rid of the titration error. On the other hand, if at all you're doing the colorimetric burette type of calibration, then of course, there will be a titration error. So going back, to precipitation type of titration, you can do many different types of quantitative analysis of different species just by converting them, into salts, where you're adding a titrant to those species to give you a salt, and then you determine, the add point, and that way you can determine the concentration of those salts. For example, you can react silver as a titrant, with all this, for example, you can take the silver as a titrant, react it with iodide, gives you the K, and you can see this K really, is equals to 1 over KSP, because the product that you are getting, is silver iodide, which is a salt, which is a precipitate. Okay, and you can see the reason why it's 1 over KSP is because the silver iodide, if you dissolve it in water, the equilibrium constant is a KSP now, which is equals to, the constituent ions, plus the iodide, and of course all of them are aqueous. Okay, so the point is, you get a titration curve like this, where you're adding the titrant to the unknown, which is the iodine in this case, and you can see as you increase the amount of silver, it keeps increasing the silver, and you get this kind of a titration curve that is there as a silver volume. As you keep adding the volume of the silver, its concentration, the concentration of the silver, you can see that's what you're plotting in the y-axis, and remember the small p refers to the negative log. All right, and so you can see the silver keeps increasing as you add the silver into it. On the other hand, you can see if we plotted instead the P of iodide, and this is volume of the silver as a titrant. Take note of this, the calibration, or rather the titration curve, is gonna look sort of as a mirror image of this, right? Because you're gonna see the iodide would keep decreasing as you add the titrant. So you can see there are 4 regions in the titration curve, before titration has happened, or before equivalence point. And then this region really, the midpoint, remember, that's the equivalence point. The midpoint is the equivalence point. And then after that, you've got, the post-equivalence, which is up here after you've consumed all the iodide, by adding the silver. So the only thing that really you're adding, is silver in water. I hope that's clear. So what are the factors, that influence analytical titrations, particularly, the precipitation types of titrations? You're going to see concentration of the analyte, is critical. As the concentration of the analyte increases, you get a better or sharper add points. And you're gonna see, this this titration curve shows that as the concentration of the iodide, increases, you're gonna see you've got a bigger gap, in the titration curve. You got a bigger gap, in the titration curve, meaning the add point, is steeper. So ideally, we are saying that we need more concentrated analyte, so that the add point is very, very clear. Okay? It's almost what we talked about with the limits of detection. If at all you've got very low concentration of the analyte, it's going to be very difficult, to see the add point. So a situation like this, if at all I've got high concentration of iodide, maybe my titration curve is going to look like that. If at all I've got low concentration, maybe my titration curve is going to look like that. And so the add point is very difficult to detect, for very low concentration, meaning the detection limit is almost getting reached, at very low concentration. Hopefully that's clear. Now the other factor, that affect precipitation types of titrations is the magnitude of the KSP. Very important. How big the KSP is. Or the equilibrium constant, which we've said they are synonymous, because the equilibrium constant, for the titration reaction is the inverse, of the KSP. I'll give you an example. Assume you're doing a titration where you've got a sample that has got iodide, it's got bromide, and it's got chloride in it, and you're trying to analyze the respective composition of all those ions. So you can do titration, using silver, where you take silver, add it to the iodide, and that precipitates. You take silver, add it to bromide in the same solution, and the bromide precipitates due to the formation of that salt and so on. And you can see, because the KSPs, are radically different, you're gonna see that the add point is much better, or is much steeper, for the iodide, because the KSP, is very, very large. And similarly, if at all the KSP is more, for example, the chloride compared to the iodide, you can see the inflection point, is fairly smaller compared to the iodide. So there's another huge factor, that determine, analytical titration is the KSP. And I hope it's clear. The larger the KSP, or rather the smaller the KSP, the bigger, the equilibrium constant, the sharper the add point. So I hope you can see that, like I've said before, you can titrate a mixture, just like we did before, with precipitating a mixture. You can titrate ions in a mixture. For example, in this case, I've got iodide. The iodide we know precipitates fast, because we know that its KSP is much, much bigger or smaller, compared to this other one, the chloride, so it's going to precipitate fast. And so you can actually detect them separately. So you can see the equivalence point, for the iodide, because it's precipitating fast. And then the equivalence point, for the chloride later on as it precipitates next. So essentially, you can see that you can analyze ions in a mixture using precipitation type of titration. So similarly, you can give an example like this, where you've got ions such as carbonates in water, chlorides in water, phosphates in water, which is very common. For example, you're trying to analyze wastewater. Often you'll be looking for these kinds of ions. And so you can use precipitation titration, where I add silver, from a burette, or using an auto titrator, to get the respective salts. And, I should be able, so that's the volume of the silver plus. and that is the concentration of the silver as I add it. And so you're gonna see the titration curve is gonna look like that, where this one precipitates first, precipitates second, precipitates last. So how do you determine what precipitates first again? Remember what we said, you simply calculate the molar solubility. And so the smaller the molar solubility, the faster it's gonna precipitate. For example, in this case, the molar solubility is that. The molar solubility of the other one, silver chloride, is that, and so on. And so you can see, the carbonates precipitates first, and then the chlorides, are gonna precipitate second, and then lastly, you're gonna have the phosphates, precipitating last. Now, because in this case you have the molar solubility fairly close to each other, it would be such that the titration reaction may not be too accurate because of co-precipitation. So you may lose a little bit of chloride when you're precipitating carbonates, and you may also lose a little bit, of phosphates when you're precipitating these, and so on, because you can see, the solubility products are fairly close, so it may not be a very accurate, precipitation type of titration. So ideally, we want the KSPs to be radically different for you to get a very accurate, type of precipitation type of titration. But hopefully it's clear, what you need to do if you have these kinds of problems. So all what I've talked about when you're using silver as a titrant is what you refer to as agentimetric titration. So if at all you've got silver, that's a B red, as a titrant, and you're trying to analyze maybe iodide in water, maybe chloride in water, maybe bromide in water, when you're doing these type of reactions, you refer to that as agentimetric titration. So the titrant, is silver. The titrant is silver. And of course, its concentration is known. Is what you refer to as a primary standard. Its concentration is known. And I think I already talked to you guys before about this. We've got 3 types of agentimetric titrations, based on the different types of indicators that they use. For example, you've got the mole type of agentimetric titration, and in this case, we use chromate as an indicator. We have the Fagen type of agentimetric titration, and in this case, you use dichlorofluorencin, what you call dichlorofluorencin. Dichlorofluorencin, as an indicator. So this one is an adsorption indicator, and this one is also a direct titration, meaning the chloride is being added, to the silver, and is a direct reaction. And lastly, you have what you call the Volhard type of agentimetric titration, and this is what you call a back titration. All right, this is what you call a back titration. And the way you do this is you take the sample, maybe it has chloride, that's what you're analyzing. You add an excess, of the titrant, so that you react, So you add an excess of the titrant so that you react everything, for the chloride, okay? And so you're going to have an excess silver that you need to determine how much is there. And then now you titrate the excess silver, and you titrate it with thiocyanate, and you get the add point, using iron, as an indicator. Okay, so this one is what you call a back titrator. Okay, where you take again the chloride, you add it to an excess of silver, and then you determine the excess silver by titrating it with thiocyanate. And you can determine how much chloride, was present initially. Hopefully that's clear. So I've talked about, using, indicators, like we said, add point creates an error, because it's always an overshot, of the equivalence point. But you can actually use instrumentation to determine the add point, so you can use spectrophotometry really to determine the add point even with precipitation types of titration. Because take note of this, if you take, say, a cuvette, it has your iodide, that's what you're titrating, and you're adding silver, okay? And then you've got, your spectrophotometer, so this one is light, that is passing through the cuvette, and then you've got the detector. So you can see, as you add the silver, you create a salt, a precipitate, the silver iodide. And so as the salt is added, as you keep adding the silver, you make more salt. And so that deflects the light. And so the absorbance, becomes less and less and less. Okay. And so you can actually plot, the absorbance, as a function of silver volume that you're adding, and you can see the absorbance is gonna keep decreasing, as you add the silver. And so you can actually use spectrophotometry, as a way to do the add point or the equivalence point detection, even when you're doing precipitation titration. I hope that's clear, that you can actually use spectrophotometry even when you're doing, titrations. And there are two types actually, of those types of spectrophotometries where you're trying to measure, the turbidity or the dissolved solids, of solution. There are those methods that you call turbidimetry, which measures the transmittance of light. And you have nephelometry, that measures light that is being scattered. And again, the difference is the location at which you position the detector. Okay, so you can see with nephelometry, you position the detector at an angle, maybe right here, relative, to the incidence. Whereas with turbidimetry, you position, the detector very similar to what you do with the regular spectrophotometry. So you are measuring the amount of light, that passes through. Hope that's clear. So essentially, it's all spectrophotometry. Both the types of spectrophotometry when you are detecting, dissolved solids or precipitates. So lastly, to conclude, you may be asked to enumerate factors that affect solubility, and we've covered them based on solubility product equilibrium. Now remember, we said common ion effect affects solubility. If at all you are dissolving a salt in pure water, it's gonna be very different than if you are dissolving it in a solution that contains a constituent ion of that salt, or what we are calling the common ion effect. And remember, we gave you an example on that. Of course, the type of solvent that you use affects solubility. I think it's fairly obvious. The temperature, of course, is critical. If at all the temperature is higher, you tend to dissolve more, and so on. pH, affects solubility as well. So you can see actually a nexus between solubility product equilibria and, acid-base equilibria, the KAB and so on. pH, does affect solubility, and of course there's an interplay between those two types of reactions, the solubility product and the acid base type of reaction. Of course, we know this is the basis, for example, of the acid rain, like I said before, dissolving coral reefs. The other thing that affects, solubility, is ionic strength. And I try to explain to you the very importance of ionic strength, when you're trying to do dissolution, but also, when you're trying to do detection using potentiometry. And I gave an example of a pH electrode where seawater containing exactly the same hydronium ion would give you very different type of pH compared to deionized or fresh water. Complex ion formation, is another factor, that affects solubility product equilibrium. And I know I didn't talk a lot about complexation, but I will do that later on, maybe in a lecture or two in the next weeks. And lastly, hydrolysis, also, affects solubility. Okay, but you got a compound that undergoes hydrolysis, you're gonna see, that that affects solubility. Lastly, you can be asked to enumerate factors, or requirements of a titration reaction. Maybe you can be asked, to design an analytical method, based on precipitation titration, or even based on acid-base titration. So what are the factors that you should be looking for, to design that kind of an analytical method? Remember, for you to be able to do a titration and do quantitative titration, of course, that is, the reaction must be of known stoichiometry. You should be able to know how many moles of the products are reacting, to give you the moles in the the moles in the products. How many reactants are reacting to give you the moles of the product? The reaction must be rapid. We already talked about that. The K must be huge. And we said as huge as 10 to power 6. Ideally, that's what you're looking for in a titration reaction. Also, the products, should be specific. There should be no side reactions. There should be a fairly neat, simple reaction that doesn't result into side products. Now you should be able to find a way of measuring the equivalence point. Very important. You need to know at what point have you consumed all your reactant, and that's what you call the equivalence point. So you either use a color indicator, of course we talked about an error in that case, or you can use an instrumentation, such as potentiometry, to measure the equivalence point, or you can even use spectrophotometry, like what I've just explained, to measure the equivalence point, for your reaction. So you should be able to have a way of determining the equivalence point. And lastly, and I think I already talked about this, that the reaction should be quantitative, it should be rapid and quantitative, meaning the K should be fairly large. So I'd like you to remember, these very important factors when you're designing not just precipitation titration, but any type of titration reaction.